then what happens? Some constant over q to the power half log square q bound beta 1 less than this. Then you have a t, you remember? There is a t in this story where the contour integration is taking place. The term t, just let's call it the term. Then the term containing beta 1, okay, in this expression, there's a term containing beta 1, say S. What happens to it? This is my term containing S, and this S is now bounded by, okay, this S is now bounded by, it's less than x by phi q exponential, and here is this my minus C3 log of x. That's the one, q to the power half log squared q. All right. Now, this one you want it to be big enough, okay? So you need the condition. You, as I said, you don't want your second main term to be, you want your second main term to be not big so that this is really an error term, okay? It really has to, you want it to be an error term when you say that. You can always write an error term, but it may not be an error term, okay? An error term makes sense only if it is smaller than the main terms. We can always write an error term. Nobody stops you from writing an error term. Is it really an error term? That's the question, yeah. And so that's what you want to control. Is it an error term? So to make this, so this one you want it to be large enough. What should you do then? What is the condition that you need? Q should be less than or equal to log x to the power 1 minus delta for a fixed positive delta. Now that is bad. I mean, to make q less than log x to the power 1 minus delta, no one can say that that's a good bound. Yeah, it's a big constraint. Okay, so the theorem as it stands here has this big constraint. Okay, the second term, yeah. What is the question? As it is written, it's correct. You just want it to become bigger than the error term. Yeah. So this will happen if yeah. It's negative, right? So yeah, this is minus. So if I write it as a negative, then the other way it becomes positive. What I'm writing here is that is only chi1a x to the power beta 1, etc. All right. So this one, when you write it as negative, if this one is smaller, then as the negative, the other one is bigger. If a is less, you have a is less than b, then minus a is larger than minus b. So this is bigger, and then when it is bigger, q is less than log x to the power 1 minus delta. Okay. So this is a constraint. Okay. This is not so good. Okay. I mean, you would like it to be, you would like more q to be included. Okay. So can we have a few minutes of break? Then I will tell you about the use of the Ziegel theorem. Okay. So what will happen when the Ziegel theorem is used is that you will see what will happen. Say 5 minutes. Okay. Yeah. নাকি জল খেতে পাওয়া যায় কোথাও আছে? হ্যাঁ, কিন্তু এটা তো আপনার, মানে আপনি কোথা থেকে খাবেন? আমি যদি সবটা খেয়ে ফেলি। আমিও ভুলে গেছি। এখানে না খুব সুন্দর মাটির বোতল পাওয়া যায়, দেখেছো? হ্যাঁ, কল্যাণীতে। আমি আজকে বিকেলে যাবো কল্যাণীতে দেখতে ওটা পাওয়া যায় কিনা। আচ্ছা। ঠিক আছে। তুমি তো এত ছোট, তাই আমি ভাবছি তুমি পিঙ্ক ফ্লয়েডের কি করে ফ্যান হলে। তো অনেকদিন আগে। ও, এটা তো ইকুয়াল হয়ে যাবে। এটা আমার ভিতরে ঢুকে যাবে। হ্যাঁ হ্যাঁ হ্যাঁ। হ্যাঁ। ও, ওকে ওকে ওকে। তুমি একটু বড় করতে চাইছো তো? না, এরর টার্মে তো তোমার কোনো এরর টার্মে তো তোমার কোনো বিটা নেই। যায়। হ্যাঁ। হ্যাঁ। তাই একটা মেইন x বাই phi q তো আছে। হ্যাঁ, ওকে 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 ওকে, হ্যাঁ তুমি ঠিক বলেছো, ঠিক বলেছো তুমি। হ্যাঁ, যাতে প্রথম মেইন টার্ম থেকে যায়। হ্যাঁ, ঠিক বলেছো তুমি, ঠিকই বলেছো। হ্যাঁ, তুমি ঠিক বলেছো কথাটা, এটা ঠিক বলেছো। হ্যাঁ, কারণ পরে আমরা যখন জিগল ওয়ালফিসে নেব তখন একটাই এরর টার্ম থাকবে। হ্যাঁ, এটা একটু মিক্সচার আছে দুটো বইয়ের। ডেভেনপোর্টে ডেভেনপোর্টে সুন্দর করে করা, মানে ডেভেনপোর্টটা পড়লে মনে হবে খুব সহজ সবকিছু, কিন্তু আসলে অত সহজ না, মানে লেখার ধরনটা আর কি। ডেভেনপোর্ট মনে হয় যে সবটা খুব সহজ, মানে গল্প বলার মতো করে লেখা। আহ, আর ছোট্ট একটা বই এইটুকুনি। আর মন্টগোমেরি ফোনটা হচ্ছে খুব মোটাসোটা, আর অনেক ডিটেল দেওয়া আছে ওর মধ্যে, মানে কোনো কনস্ট্যান্ট ওরম ছেড়ে দেয় না আর কি ওরা, ওটাকে তারপরে ওটাকে কতটা এক্সপ্লিসিট করে লেখা যায় সবকিছু লেখে, সেটা তখন ঘুম পাবে না অত সহজে ওটা নিয়ে। কিন্তু ডেভেনপোর্ট নিয়ে বেশ তারপরে তোমার ডিটেল গুলো দেখতে হবে যে আর কি কি করে কি কারণে বলছে আর কি কথাগুলো। কিন্তু একটা ঘটনা হচ্ছে যে ডেভেনপোর্টের যে ইয়েটা, ইন্ট্রোডাকশনটা, না মানে নতুন এডিশন যেটা বেরিয়েছে সেটা কিন্তু মন্টগোমেরি লিখেছে। কাজী 23 থেকে 29 ওই বইটার যেটা শেষ সব চ্যাপ্টার, সেটা মন্টগোমেরির লেখা। যে রিভাইজড বাই, থার্ড এডিশন যেটা, সেটা রিভাইজড বাই মন্টগোমেরি। শুরু করবো? আচ্ছা, আমাদের সব এই যে আমাদের কথাবার্তাই সবই কি রেকর্ডেড হয়ে যায়? আচ্ছা, জল খাওয়া টাওয়া সব রেকর্ডেড হয়ে যায়? আচ্ছা। So when we wrote the first theorem, there was a constant, you remember, and we called that constant C1. So you might have wondered why we began the course calling it, giving it a subscript. The reason is that we will use it. I wanted it to be kept separately so that we can use it and say that that is the same. I don't know whether we named the theorem anything. Did we name the theorem for the explicit formula? Okay. In the explicit formula, there is a C1. Yeah. And that's the same one which we will now use in this new result. Okay. Where we will assume Ziegel's theorem. Okay. So we recall, first of all, that beta 1, there exists 1 minus c epsilon and q to the power epsilon. Yeah, there exists for every epsilon, there exists a constant that depends on epsilon, such that beta is less than 1 minus c epsilon by q epsilon. This is Ziegel's theorem from 1930. All right, and now we will show a corollary, not of Ziegel's theorem. I mean, it uses this, but it comes from the explicit formula. Okay. So corollary of the explicit formula is which I should have given a name to it. You can maybe give it a name. It was the first thing we did today, okay, of the explicit formula. You could call it, you could give it a name to that theorem, okay? So, so if I take any positive A, then there is some x0 which depends on A such that Q here is less than equal to log x to the power A. All right. Then that's a reformulation. Then the explicit formula psi x chi is equal to E0 of chi times x plus big O of x exponential minus C1 square root of log x. Okay. For what? For all x greater than or equal to x0. Okay. So let's see how we prove this. Proof. If chi is quadratic, and LS chi has an exceptional zero, which I call beta 1, then what happens? x to the power beta 1 is equal to x exponential minus 1 minus beta 1 log of x. There are too many. Which is less than or equal to x. I wanted to say something. C1, where is my, this C1 is the constant in the explicit formula. All right. So so now I can use the fact that this can be bounded by minus C epsilon Ziegel q to the power minus epsilon log of x. Yeah. So this is Ziegel. And this, let's take another color. Okay. However, q is less than or equal to log x power a. Okay. So use that. If q is bounded by log x power a, then this one is bounded by here. This is bounded by x, so from here I come, less than or equal to x exponential minus c epsilon log x to the power 1 minus a epsilon, which is less than or equal to x exponential minus c. This c is the c of this c, okay? Not the same, not necessarily the same one that comes from the explicit formula. Square root of log x okay. So for every epsilon, I can do this. So I take epsilon to be equal to 1 by 2a, okay, and x to be greater than or equal to x0, which is the x of C1 and C0, C epsilon to the power to some power. Okay, and then we are done. Okay. So I want to Now state, now I want to state a quantitative form of the prime number theorem. So you know that qualitatively we know that there are infinitely many, and quantitatively what can we say? So for this, here I will state it as with the von Mongold, and then we can go back to the pi. Okay, so here is the Ziegel-Wolfis theorem. Okay. So again, I will let C1 be the constant in the explicit formula. Okay. We will fix a positive, that A that we had. Okay, where is it? Here. Let us fix an A. All right. So now you let Q to be less than or equal to, here, Q is less than or equal to log x power A. A and Q are co-prime. Then I can state the Ziegel-Wolfis theorem now, which is not in terms of x pi, but in terms of x, q, and a. So psi, okay, we'll state it here because on this side. xqa. You remember the main term. This is x by phi q. And then I take in everything into my error term. So what is it? X, I get an x. I get an exponential of what? Of that C1, remember? The C1, there's a C1 and there's a square root of log x. And this depends on the A that we fix. All right? So that's the Ziegel-Wolfis theorem. And so now the range is Q is less than equal to log x to the power capital A. However, there is the fact that we have lost the effectiveness. Yeah, what we have gained for the range but lost in effectiveness. Yeah, so the choice is yours. Yeah, yeah. 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 This is with the XQA, and the other one was with X chi. That was for the 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 corollary.
Okay, depending on the character.
That depends on the character. Yeah. And this is when it is like when we first had the explicit formula, how we got an asymptotic for.
Okay, that was for quadratic character.
Yes. Okay. And this is XQA. So so the universal bound that we if you want an universal bound, then, well, you lose in terms of the effectiveness of the constants. Yeah. So now from here, if you have the Ziegel-Walfisz theorem, you can also prove the prime number theorem. So instead of writing it, so theorem, this is the prime number theorem. I mean, that's what we were supposed to find, yeah? So this is the prime number theorem in arithmetic progression. Which means now we will not state the result in terms of psi, but in terms of pi. Yeah, just as that's how you did it for the prime number theorem, the usual prime number theorem also. I think the prime number theorem is something that everybody knows, but the prime number theorem in arithmetic progression is maybe something that not everybody knows. Everybody means everybody on the streets has heard of the prime number theorem, right? Do you know anyone who doesn't know the prime number theorem? There is no such person. Everyone knows the prime number theorem. But not everyone knows the prime number theorem in arithmetic progression. For that, you're special people who have seen the proof and you know it. Yeah. So again, we will have the same conditions. So I'll write it out nicely. Again, I will take C1 to be the constant in the explicit formula, and I will take A and Q to be co-prime to make my definitions. And then so now I want to write, I gave a definition right in the first, remember that? Pi of x q a, it's equal to the number of primes that are less than x. P is congruent to a modulo q. So this has not been smoothed out by lambda of n. Okay. Then pi of x qa, this is equal to the logarithmic integral x divided by the normalizing phi q plus big O exponential minus C1 square root of log x. This with the same C1. And when there is, this is one case. This is the case when there is no Ziegel zero. All right. And if there is a Ziegel zero, which is beta 1, and occurs then pi, and there is no Ziegel zero modulus q, okay? Otherwise, it is equal to the logarithmic integral by phi q always, and then comes a term which will involve the betas. So this is chi1a. Chi1 is the exceptional character. The logarithmic integral x to the power beta 1 and phi q plus, I get the big O again, exponential minus c1 square root of log x if beta 1 is an exceptional 0 and chi1 the exceptional character. So maybe this is how you had seen your, this is how the, so you see if q becomes equal to 1, then do you recover the prime number theorem? Yeah, you recover the prime number theorem for at least, I mean, it's one way of writing the prime number theorem. This is the way that de la Vallée-Poussin, I think he wrote it in this way. Because you know that prime number theorem was not proved jointly by Hadamard and de la Vallée-Poussin, but separately. They were both working on that, or a lot of people were working on that. But we always say prime number theorem was proved by de la Vallée-Poussin and Hadamard, but they didn't do it together. So there is if you go back and read the real papers, those papers, you will see that they are stated in not necessarily exactly the same manner. So the way that when q is equal to 1, this you get back the statement of so this is a generalization of the prime number theorem as stated by de la Vallée-Poussin. Okay, Hadamard did not state it like that. So then he wrote it with exponential. This, and then the second case does not come, right? Because of course, when you have zeta functions, you don't have Ziegel zeros. Okay. So do you know how to reach from psi to pi? So how do you go from psi to pi? It's the same way as you did for zeta. You want to imitate the proof? How do you go from, that is the, we wrote the result for psi and then we wrote the result for pi, but how do you come from psi to pi? That is, how do you come from von Mongold to the counting function? Yeah, you must have seen that. You did that with them. Yeah? So how do you do that? You don't have your So for that, okay, so you can take a third function, that is you have pi, you have psi, and you have theta. Yeah. So so let theta, it's x qn of a. This is equal to, instead of lambda n, we take it to be sum of log of p. Okay, and p is congruent to p is less than equal to x, and you have a congruence condition a mod q. Yeah, p is congruent to a mod q. So you can integrate the Siegel-Wolfis theorem by parts, and you imitate the proof of, so pi of x, how do you come from psi to pi? So you do this via theta. Okay, so maybe you can do that yourself. So you can express pi in terms of theta. So if you do that, pi of x qa, how would you write this in terms of theta? So theta is, this takes the sum of log of p. So you have a log p, which is, you have a 1 by log p. So we won't call it p, we'll call it u. And then you take the derivative u q of a, and you integrate this. Yeah. So, and you get back pi. So what do you get as the first term if you do that? What comes out as the first term? There are you imitate the proof for the prime number theorem. Okay. So the main term comes out as the logarithmic integral Lix divided by phi of q. Okay. And then you have another integral which is 1 by log u d theta u q a minus u by phi q. And this goes between 2 and x. Okay. Now integrate by part. If I integrate by parts, then this one, theta u q a upon log u take it between 2 minus an x, and you will get back your prime number theorem. Okay? You can finish it, the last line. Take a product of two functions and integrate it. That is something usually not complicated, can be done. Yeah, is there something different with the prime number theorem here? No, nothing is different. It's exactly the same proof. You can copy and paste. So in the afternoon, we will do some exercises. As I told you that the problem with this is that you don't get the good range. Either you don't get the good range or you don't get a good effective constants. So because of the presence of Ziegler zeros. So either one or the other is a problem. So if we take some conditional results, that is, if we assume, for example, the generalized Riemann hypothesis, then things will become nicer. And we can do a little bit of that as exercises this afternoon. These will be generalized. These will be conditional. Conditional. Either it can be for the explicit formula, or it can be for the prime number theorem. Okay. And we can do a few such questions in the afternoon.